All right, let's take a look at exponential growth and decay, and I'm going to take the differential equation perspective to kind of describe where this exponential function comes from and even what it means to be exponential. So this is what it says, dp dt equals kp. Let's translate that to what it really means. This says that the growth rate of the population is proportional to the population. So as the population gets bigger and bigger and bigger, the rate of change, meaning the people per year, will also increase and increase and increase. And what we're claiming is that this describes an exponential. And again, if you're graphing P versus T, if you had some exponential population, it would look like this. It'd zoom away really, really fast. Okay, and let's go ahead and show that this is true. So how would you solve this? Again, anything of the form, it doesn't matter if it's a P, it could be a Y and X, but dp dt equals kp. That's saying that the derivative is proportional to the actual function, meaning the slope is proportional to the y value. That means it's exponential. We can solve this. Doesn't take long to separate. So go ahead and divide by p, multiply by dt, integrate both sides. That's a dp, it's not great. So the integral of dp over p is the natural log of p, and I'll use absolute values. Again, we're not really going to look for any negative case, plus some c. Then I'm going to exponentiate, which means if these two things are equal, e to that same power also has to be an equation. E to the natural log of p is just p. I'm going to go ahead and drop the absolute value. And then I have e to the kt plus c. And you have to remember your exponent rules. If you had something like e to the a plus b, that's the same thing as e to the a times e to the b, right? When we multiply with the same base, we add them. I'm going to go the other direction. So e to the kt plus c is really just e to the kt times some e to the c. C is just a number, so e to the c is just another number. And the cool part here is that it does actually represent something. It represents the initial population. This e to the c is just the original population, which we'll call p naught. Again, why does that? Why do we know what this is? Well, because if I let t equal 0, this is going to go to 1. So whatever number is here, it will correspond to the population when t equals to 0. So that's what it is. It's the initial population. Again, this is what you've probably learned about exponential growth and decay. That's some sort of function. Some people call it the PERT function, where there's an R here instead of a K. But I want to make the argument that this is more fundamental to exponential growth and decay than this is. This is really describing what type of growth exponential is. It says that the growth rate is proportional to the population. Okay, what does that mean? Okay, let's take this scenario where we had dp dt is equal to 0.1 p, right? This is a 10% growth rate, kind of. Okay, so if we know if the population were 20 people, then p prime, right? P prime is dp dt. I'm just going to save myself some notating, is 2. And again, that's 2 people per like a year in this case. Well, what if p was 100? So our population is bigger. Well, p prime is then 10 people per year. What if p prime was, my bad, not p prime, just p, is 500? Well, then p prime is 50. So do you see how the growth rate is always just going to be 10% of the population? That's what this says. The growth rate is getting bigger and bigger and bigger. Now, it's still growing by a percentage. That's what it means to grow exponentially. It's like investing money and getting 10% on your money compounded continuously. You're always getting a constant rate of 10%, but the actual growth rate of your money, meaning how much dollars you get per year, gets bigger and bigger and bigger as your bank account gets bigger and bigger and bigger. I mean, $2 is 20% of 20, just like 50 is 10% of 500. But once you got $500 or 500 people in a city, you're going to start growing by 50 people per year. That's what it means to be exponential. And how do you know it's growth? Well, think about it. If k is positive, right, then you're going to get some exponential growth thing, meaning you're going to get a positive exponential that's going to look like this. If k would be negative, you wouldn't change anything. This would just be a negative, and we know that exponential decay, like radioactive decay or a city dying or a company, losing revenue exponentially, that would really be bad for a company. And again, look at the slopes here. What's happening to the slope? Well, we're claiming that the slope is proportional to the population. Look what happens to the slope. Slope is, I don't know, maybe 1, then 2, then 3, then zoom. The slope gets bigger and bigger and bigger as the population gets bigger. Same thing here, except it's the opposite. What happens in decay? Well, look at the loss of people. The city lost a ton of people, and then didn't lose much, and then didn't lose much at all, and then barely lost any. Well, because as the population gets smaller and smaller, so does the loss of the population, meaning the decay. And that's how everything works when it's exponential. Again, it's a percentage thing. You lose a lot of, take 1,000,000 people and you've lost 10%, man, you're losing 100,000 people. But once your population got down to 100,000 and you only lose 10%, well, then you're only going to lose 10,000 people. Again, the rate of change is proportional to the population. This happens all over the world, whether it's chemistry, biology, finances, economics. Exponential growth and decay all have this exact same pattern. You know that this means this because it doesn't matter what k is. K can be any number you want it to be. It can be negative, it can be positive. This differential equation leads to this solution. And again, so hopefully you're going to start to recognize different things in different even subjects other than just calculus of how this restriction leads us to this relationship, and then we know that exponentials have kind of certain properties.